Oh, good afternoon, good evening, good morning. I wish I knew what time it was. This feels weird, still talking to a microphone on a computer. I'm used to seeing real people in front of me. But seriously, thanks for checking in. This is approaching the end of chapter 14-ish on acid-base equilibrium and asking the question, if I dissolve a salt into water, will it be acidic or basic? And the answer is, that depends. Let's look at a couple of charts. This is a qualitative prediction of pH for acid-base nature of salts. This is true, but it's sometimes hard to tell just by looking at it without a lot of experience how the Ka and the Kb for a particular acid conjugate base, base conjugate acid pair relate. But we know the pH is lower than 7 acid, higher than 7 a base. And in a sense, eventually we might compare some Kas to some Kbs. I might also post this little chart on my PDF, but honestly it's confusing me. So here's the way I like to look at it. Let me say, do you know your strong acids and your strong bases? And of course, only you can answer that question. But they're really handy to know, because if I know my strong acids and I know my strong bases, I know everything else is weak. And why do I care? Because here's the deal. If you know strong acids and strong bases, you know that all this, and you don't know this yet, I'm telling you, but you will know. I'm telling you that all the salts you can possibly make from all the strong acids and the strong bases, all of many different combinations, those are neutral salts. They don't have any acid-base nature to them at all. If this is a super strong acid, its conjugate base is very weak. If this is a super strong base, its conjugate acid is very weak. True, OH minus, the base, water, is the conjugate acid, very weak. In any case, bromide, iodide, nitrate, perchlorate, sulfate. Sulfate's a bit trickier because, the first hydrogen comes off well, but the second one doesn't always come off so well. But I'm trying to say is, take anything from this column as in terms of the positive cation, which counterbalances the strong base, hydroxide, and anything over here, which is the negative part, which counterbalances the positive H+. And any combo from here and here will give you a salt that's neutral in the water. Let's see if I can say that in a different way or throw another twist on it. I can't. But I've only written a few here. Like, what about cesium? What about cesium iodide? Would that be a neutral salt? What about cesium bromide? What about barium chloride? What about strontium iodide? You get the idea. Take anything from here, any metal from the strong bases, and any non-metal or non-metal combo from the strong acids, and voila, you have a neutral salt. A salt that has very little acid-base nature to it. Like I said, the sulfuric acid's a little bit trickier in the sense that the sulfate ion does interact with the water a little bit to create this. So this would actually be a better question, a better statement of, this is sulfuric acid, it's strong, but the conjugate base of sulfuric acid is HSO4 minus, the bisulfate or hydrogen sulfate. So that salt in the water would definitely be neutral. All strontium salts are neutral. Well, unless that negative part comes from a weak acid, not a strong acid. We'll get to that in a second. Or what about lithium perchlorate, neutral, or lithium bisulfate, or lithium nitrate, lithium iodide. Again, take your pick. Anything from this column, anything from this column. The combo is a salt. They sell it to me in a bottle in the supply room, and they can weigh it on a scale. But again, these salts are all neutral. But what about the salts that aren't neutral? That might be more interesting. Here's one, ammonium chloride. Ammonium salts are always interesting because the ammonium NH4 is the conjugate acid of ammonia. So this, I might think to myself automatically, is some kind of an acid. What about iron chloride? Well, the chloride comes from here, but where does the iron come from? It's not listed on my list of strong bases, so I'm pretty sure it would be acidic or basic. I don't know. I know, but I'm going to say in a minute. Cobalt chloride. Chloride looks good. Cobalt, cobalt. There's no cobalt over here. So I'm pretty sure this positive cobalt ion in the water would function as an acid. But anyways, vanadium 4 bromide, copper 2 iodide. So I have iodide. That looks good. That negative iodide would be neutral, but the copper would not be neutral. Zinc nitrate. Oops, I forgot my little 2 there. Subscript. Zinc's a 2 plus charge. I have to fix that on the PDF. There's a little 2 here, you know. Zinc nitrate. Zinc 2 plus, nitrate single minus, 2 negatives. 2 negative nitrates to match up with the zinc. Nickel perchlorate. Well, there's the perchlorate, so it would be, that part of it would be neutral, but the nickel part, not so neutral. There's a famous professor here in the department. He's actually retired recently. His initials ROR. Genius. He said that any cation, positive ion in the water, could possibly function to be acidic, or at least be a Lewis acid. Let's try it. Here's ammonium ion. Yep, there it is. It's acidic. Iron 3 plus iron. A weird thing happens. Here, a little bit weird. What happens is the positive of the iron attracts the OH minus group on the water, and at least one of those OH minuses is probably ripped over onto the iron ion. The smaller the ion and the more positively charged the ion, the more it's able to do this. So actually iron 3 plus might rip off 2 or 3 of those, probably at least 2 hydroxides, 2 waters apart. And I create this. There's the H plus of the acid. So by the Lewis definition, there's no way that's an acid. I'm sorry, by the Arrhenius definition, there's no way that's an acid. I don't see any H plus there. But certainly by the Lewis definition, it's an electron pair acceptor. It accepts the electron pairs on the oxygen. Same for vanadium. Very small, very highly charged ion. Can pull that water apart pretty easily. Interesting definition of acids. Let's do some more. That was so much fun. Also non-neutral salts. Lithium. Yep, that's neutral. Sodium. Yep, that's neutral. Ions. Potassium. Neutral. Cesium. Neutral. But I chose these negative ions that are not part of the, strong acid anions. So acetate, don't see it. Lactate, don't see it. Propionate, don't see it. Benzoate, don't see it. So even though these first positive cesium, potassium, rubidium, sodium, lithium, even though the positive cations would be neutral, in this case the negative anions would not be neutral. Let me go. I got more examples. Wow. Let's see. So the iodate, the barium part would be neutral. It comes from the strong base, but the iodate does not come from strong acid. So that part, that negative part, and this negative part, the cyanide ion, they would have some interactions with the water. Again, quoting, any negative anion in the water could possibly function as a Lewis base, in a sense ripping the water apart. Because if I have a weak acid, this is a fairly strong conjugate base, and the weaker the acid, weak acid, weak acid, weak acid, weak acid, the stronger the conjugate base. I'd have to look at constants for those weak acids to tell you how strong the base is, but still, they all could possibly negative, 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 even if it doesn't have a negative, as long as it has a lone pair, could quite easily and possibly attract the hydrogen ion off of the water. Interesting. Amphoteric ions or salts with competing ions in solution can be very tricky. Let me show you 1 or 2 of those. By that I mean, what if I had the positive cation from a weak base and a negative anion from a weak acid? That would confuse me. Let's try a few. For amphoteric ions in solution, we look at the Ka versus the Kb, but you got to be very careful about how you calculate Ka and Kb. Here's baking soda, sodium hydrogen carbonate. Let's see. So here's the baking soda anion, Sodium is from sodium hydroxide. That's a spectator. It's not strong. It's not as strong. It doesn't have acidic or basic properties. But what about the bicarbonate? So I wrote this equation, and I wrote this equation. This is Ka. There's the hydrogen on that one, but it could possibly come off. But it came from, you realize this? It came from carbonic acid, the full-blown H2CO3. And so the H2CO3 created this, and the chance, the probability, the degree to which the second hydrogen dissociates is described by this small number, eh? That's small. All right, so what's the other possibility? This is functioning as an acid here, but how could it function as a base? Well, as you might remember, most weak bases in the water actually interact with the water, pulling the water apart. So the negative here attracts the positive there, creating the OH minus. This is called carbonic acid, the conjugate acid of this base. So if I know the constant for this H2CO3 dissociating to go back this way to give this, that's the Ka. So the Ka1 for this acid is larger than the Ka2 for the acid, and the Ka1 for this acid is associated with the Kb for this. In a sense, you could call this the acid and this the conjugate base, or this is the base and this is the conjugate acid. Doesn't matter how you pair them, but they are conjugates of each other. And to find Kb for this base, I take Kw over Ka. In other words, the product of these two is 10 to the negative 14. Interesting. Now that I know the Kb for this, I can compare it to the Ka for this. Let's see. Ka for this, Kb for this. Which one's larger, 10 to the negative 8 or 10 to the negative 11? 10 to the negative 8. So since the Kb is bigger than the Ka, I'm going to say it's basic. The basic, because 10 to the negative 8 is larger number. What is it? 1, 2, 3, that's 1,000 times-ish larger than this number. Wow, that's trippy. Do we have time for one more? Maybe. What about the ammonium hypobromite? I have no idea. Well, let's see. Ammonium, in a sense, comes from ammonia. So the Kb for ammonia, you'll find that in the tables all over, but you'll never find the Ka for ammonium ion, because most chemists know you just calculate it. Just take Kw divided by Ka. So here's my, by Kb. This is my base. This is my conjugate acid. What's the Ka for this conjugate acid? Again, Kw over Kb. Interesting. What about the anion part? The hypobromite ion? Might pull the water apart. I have a Ka for this acid, HOBr, but I don't have a Kb for this base, but I can pretty easily calculate it. Same fashion did up here. Whoa, take a look at that when you get time. So the conclusion is, which is bigger, 10 negative 10 or 10 negative 6? And the answer is 10 negative 6. So guess what? It's basic again. This one's basic. Although it totally depends on what the relative sizes of the constants. That's what I wrote there. Let's see. Is that going to do it? I think that's going to do it. Is that going to do it? That's going to do it. I have part 2 of this, but it'll take a little bit longer. So thanks for watching, guys. Thanks for all your hard work. Keep it up, and I'll see you in class.